This video, we're going to pick up where we left off last time in 4.3, and we're going to talk about some application problems here that require us to look at minimums and maximums of these exponential functions. So let's go ahead and look at number 43 from the textbook. And this is going to be a catenary. And the equation for it is 25 e to the x over 50 minus e to the negative x over 50, and x is between negative 25 and 25, so that the poles here are at 50 feet apart, and we want this to come down and go back up, and the halfway in between here is 0, and that's where we want the low point to be. But this is like a wire dangling between two poles here, and it's going to reach a low point, and that function is going to represent a hyperbolic sine function here. So no. Yes. So let's go ahead and find the derivative. The derivative of that should represent a hyperbolic cosine function. One over 50, negative 1 over 50. It's going to be a plus. Oh, this was plus to start off with, and this is minus. That's why I was saying that that looks like hyperbolic cosine. That's right. So this is going to look like hyperbolic sine when I take the derivative of it. There we go. And again, that was from a 1 over 50 here and a negative 1 over 50 here. Pull the 1 over 50 out with a 25 on top. 25 over 50 is 1/2. I'm going to set that equal to 0. The 1/2 can't be 0, so I'm going to set this part equal to 0. And I'm going to get e to the negative x over 50 comes out and gives me e to the x over 25 minus 1 equals 0. I'll just leave the 1/2 out here for the moment. This part can never be 0. Or this part is 0, and that can only happen when e to the x over 25 is equal to 1. Take the natural log of both sides. X over 25 is equal to 0. X is equal to 0. So we've shown what we wanted to with part A, that the minimum has to happen at x equals 0. Let's use our first derivative test to prove it, though. That here's our first derivative. This piece is always positive when I'm to the left of 0. This piece is going to be a fraction. It's going to be smaller than 1 minus 1. That's going to give me a negative times a positive piece is going to be a negative over here. So it'll be decreasing to the left of 0. When I'm to the right of 0, this piece will be a number greater than 1. And minus 1 is going to be a positive number. This is a positive number that's a fraction here. So this is going to be a positive number here. And so it's increasing to the right, decreasing, then increasing, says that there's a local min here. Again, use your calculator if you need to confirm that this side has a negative slope and this side has a positive slope, and you want to stick some test points in that are negative numbers and positive numbers. But it'll work out that way for the derivative. Now we want to use a graphing utility to graph the function and verify our answer from part A. So let's go ahead and do that. I think I might already have that in here. I do not. So 25 times e to the x over 50 plus e to the negative x over 50. And we're going to go from negative 25 to 25. We can go by ones. And I don't know how tall this will be. I'll go from 0 to 100 by 10. So let's see if that's good enough. There it is. And so we have a low point right there. And let's confirm it. Second calc minimum. And that says times 10 to the negative fifth. So this is 0.00001. The calculator is just a pixel error. That's really 0, but it says that the y value is going to be 50 because I'm going to get 1 plus 1 is 2. 2 times 25 is 50. Okay, so is parts A and B for number 43. Part C asks us to say how much does the cable sag between the two towers. So I want to find this was part B, was to graph this and show that this point was at 0, 50. Part A was here. Part C, I want to find delta y, which is going to be y of 25 minus y of 0, because the maximum is going to be here at the end. And I could use either end, it doesn't matter, but I'm going to come in here and say vars, y vars function y1 of 25 minus vars, y vars, y1 of 0. That's exactly what I have right here. I'll let the calculator tell me that delta y is approximately, and we have going to the nearest tenth of a foot here, 6.4 feet. There's no reason for you to calculate all that by hand when you have it in your calculator and you'd be sticking it in there anyways. Just use the function that you already put in and use your vars menu to help you calculate that. Let's look now at number 44. Number 44 asks us to maximize revenue when we have a demand function P equals 73e to the negative 0.000025x. Okay, so when we have a demand of 0 items, the price is still 73. As demand goes towards infinity, the price is going to go towards 0, but it's not ever going to get there. Our revenue function then, R is going to be XP, so that's going to be a 73x e to the negative 0.000025x. And we're going to have to use the quotient or the product rule here to find r prime. So r prime is going to be 73 e to the negative 0.000025 x plus, and then 73x times a negative 0.000025 times e to the negative 0.000025x. So that is going to turn into r prime is 73 e to the negative 0.000025x. I'm going to multiply here 73 times a negative 0.000025 is a negative 0.001825x e to the negative 0.000025x. So let's go ahead and let's factor out here that this is e to the negative 0.000025x times 73 minus 0.001825x, like that. And when I set this equal to 0 to optimize, then I'm going to get e to the negative 0.000025x equals 0, which I know can't happen because that's an exponential function. It'll get close to 0, but it'll never get there. Or 73 minus 0.001825x is equal to 0. So when I solve that, negative 0.001825x equals a negative 73. Negative 73 divided by negative 0.000025x equals 292,000. So we would need to sell 2,920,000 units to get this demand here. And I think that's right. So 0018 yes, 1825, yes. All right, so, oh, no, I didn't put the 1825 in there. So negative 73 divided by negative 0.1825. I say that number seems way too big. 0.001825. There we go. That sounds better to me. That is 40,000 units of demand. All right. So we have 40,000 units of demand, and then going to prove that that maximizes my revenue. So there's 40,000. If I pick a number, let's stick the revenue equation in here. or the derivative of the revenue equation. Let's just stick it in here to prove to ourselves that your 73 x e to the negative 0.000025 x, and I'll show you that if we graph this, let's go from 0 to, I don't know, 100,000 by 1,000, and 0 to, I don't know what my revenue should be, maybe have an answer here for how much I would sell at that point. So let's make this big. Let's make this 2 million. Let's go by increments of 100,000. Okay. That, there's the graph. And I want to find this maximum point for you in just a second. But before I do that, and show you that that is at 40,000, let's find the slope here at a number less than 40,000, like 30,000. There, and you're going to see that it has positive slope. You have positive slope over here when x was 30,000. And let's go over here to the right of 40,000, like 45,000. So second calc dy dx, let's go to 45,000. And you'll see that it has negative slope there. See the dy dx right there is negative. So that's going to be positive. The negative is increasing and then decreasing. So there's a local max here, just like I expected. And then we will go ahead and use the calculator to verify what we think the local max is. But let's go ahead and figure out what revenue we get when we have $40,000. So quit vars, y vars function y1 is our revenue function, 40,000. And so we're going to have R of 40,000 is equal to 1074207.97. You have to round to the nearest cent there, but we're asked, so that was part B, but part A asks what price will give us that. So we want P of 40,000. And let's go ahead and just figure that out on the screen. 3 second e to the negative 0.00025 times 40,000 is $26.86. Okay, so when we sell these for $26.86 per unit, we'll sell 40,000 of them and we'll make $1,700,000 $74,207.79 for our maximum revenue. Let's look now at number 45, which is a depreciation problem. Depreciation of assets is an important concept in business. You usually will take the loss, the depreciation loss, as a tax deduction lots of times. So the value V in dollars after the item is T years old is given by V is 15,000 e to the negative 0.6 286 times T. So this thing never loses all of its value is what this is saying. But it started off with a value of $15,000 and it will continually depreciate here. So, but they're telling you that we're only interested in the first 10 years here. That's probably because that's the amount of time that you can write off the depreciation for it. So let's sketch the graph of that with the graphing calculator. So the first thing they want us to do, 15,000 e to the negative 0.6286, and I'll use an X instead of a T. Window is going to go from 0 to 10 by ones, and then its maximum value that it should have here is going to be 15,000, and its minimum value, it can't go below 0, so 0 to 15,000 by, let's say, 100s here, graph like that. And we see a steady depreciation curve like that, a exponential curve with a negative coefficient on the X. So sketch the function there. So 0 to 10 here, just a steady depreciation curve like this. And I need to know at 10, this has a value here that's not quite at the x-axis. It's 2793. It's how much value it has left. And up here at x equals 0, it actually has a value of 15,000. It starts up there. So find the rate of change of V after 1 year. Use my calculator to do that. Second calc, 6 at x equals 1 is going to be negative 5,028.84 dollars per year. So and if you want the math for that, V prime is 15,000 times negative 0.6286 e to the negative 0.6286 t. So V prime is going to be a negative 9429.0 e to the negative 0.6286 t. And then V prime of 1 is going to be negative 9429.0 e to the negative 0.6286. V prime of 1 is about negative $5,028.84 per year, which is what I let the calculator do for me. Then it asks to find this is part B. Find the rate of change after 6 years. Equals. And so I'm going to come in here, second calc, number 6, when x equals 6, I'll find out that this is negative 217.01 per year. So it's still decreasing, but it's decreasing at a decreasing rate. And again, you can go ahead and stick that 6 in here. V prime of 6 is going to be a negative 9429.0 e to the negative 0.6286 times 6. If you want to stick that into your home screen there, you will get this negative 217.01 when you round to the nearest cent. I just let the calculator use its slope at a point feature for me, since that's what I'm being asked for. Let's go ahead and look at number 46 from the textbook next, which is a how do you see it problem. So you'll need to be looking at that picture that is available for you there. Just a second. $46. And so when you're looking at that picture, the yield Y in pounds per acre of an orchard of age T years is modeled by Y is equal to 7955.6 e to the negative 0.0458 divided by T. I'll just go ahead and graph that in my graphing calculator so you don't have to look at the textbook for that. So 7955.6 e to the negative 0.0458 divided by x instead of divided by t. And my graph here goes from 0 to 15 by ones and goes from 7,000 to 8,000 by 100s. That's the only part of the graph that I'm interested in. So they just do a little lightning bolt thing between 0 and 7,000 to say, I'm not showing you that part of the graph. We're not interested in it. So there's the graph, what happens to the yield in the long run. So out here, it looks like it's leveling off. Let's prove that. Limit as t goes to infinity of y is equal to limit as t goes to infinity of 7955.6 e to the negative 0.0458 divided by t. As t goes to infinity here, this exponent is going close to 0. So 7955.6 e to the 0. It's going to be 7955.6 times 1 is 7955.6 Is this money or is this, no, this is pounds. So our yield is measured in pounds per acre. So pounds per acre is what that's going towards. And then it asks what happens to the rate of change in the yield in the long run. So if I were to find y prime here, which is 7955.6 times negative 0.04 8 times negative 1 over t squared times e to the negative 0.0458 over t. That limit, let's figure out numerically what some of that would be, just to clean things up a little bit. I know some numbers really don't matter, but let's clean it up as much as we can. 0, 4, so it's 458. Times a negative 1 is going to be a positive 364.3664 e to the negative 0.0458 over t over t squared. So when I do that, this is e to the 0 in the top, so this is going to that constant. Over infinity squared will be infinity. And so that constant divided by infinity is going to go towards 0. If you want to see what that looks like here, as we go to infinity, 364.36648 e to the negative 0.0458 x, and all that is divided by x squared. I'm going to zoom 0 on this. We're going to see that it's a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0, that we're getting closer and closer to 0 change. And we saw that on our graph of our original here, as we graphed y originally, that it was a function that was going up and to the right, but it was increasing at a decreasing rate, and the slope was becoming more horizontal, getting closer and closer to 0. Look at number 47 now, which is a compound interest problem. Number 47 asks us to use the equation A for our accumulated balance is 5,000 e to the 0.08t. So what that tells me, I deposit $5,000 and there's continuously compounding interest at an 8% interest rate. And I want to find the accumulated balance. So might as well just use my calculator to do this. 5,000 e to the 0.08. Now I use an x instead of a t. They want to give me several different times here. So I'll make sure that my independent is set to ask. I'll go to my table here, and they want to ask me, well, how much do I have after 1 year? And so A of 1 is going to be 5416.44. And then I'm going to make a chart here for A and dA dt. So A of 10, and I'll get the other values in just a second once I get that equation, is 11,127.70, and then A of 50 going to be, just want you to see how quickly this builds. 27,299.75. All right. And now I want the equation for dA dt. So that's going to be 5,000 times 0.08 is 400. E to the 0.08t. Let's plop that in here. 400 e to the 0.08. And it's going to calculate this for me. So dA dt at 1 is $433.31 per, and I'm going to say that that's per year because t is measured in years. And then dA dt of 10 is $890.22 per year, and dA dt of 50 is $21,839.26 per year. So let's look at number 48 next. Number 48 is about learning theory. That says the average typing speed, capital N, which is in words per minute, after T weeks of lessons is modeled by capital N is equal to 95 divided by 118.5 e to the negative 0.12 t. So as that exponent, as time goes up there and that exponent becomes more negative, that comes across, and that exponent becomes positive. It's a bigger positive number in the numerator, and you should be able to type more words per minute. but you may not necessarily be learning them at a increasing rate, right? So we're going to see where this, where your rate of change kind of tops out here. So we want to find n prime. N prime is going to be, let's write this as 95 e to the 0.12 t over 118.5, and we'll leave that 95 over 118.5 alone because there's no t out there. And we'll have times negative 0.12 e, sorry, this is up in the top now, 0.12 t. Oh no, that's not what this says at all. This is 1 plus 8.5 e to the, okay. So this is 95 e to the 0.12 t over 0 e to the 0.12 t plus 8.5. All right, that's better. And then I have to use the quotient rule. So derivative of the top, 95 times 0.12 e to the 0.12 t over, let's see, derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. I really don't care a whole lot what that is. I'm going to simplify it a little bit for you just to make it easier for you to type it into the calculator. But we're going to be typing this into the calculator. So n prime is 11.4 e to the 0.12 t times e to the 0.12 t plus, so that's going to be e to the 0.24 t plus 8.5. Let's see, 11.4 times 8.5 is 96.9 e to the 0.12 t minus 11.4 e to the, this and this are opposites, 95.12 equal and opposite signs here. So I just get left with that part over t plus 8.5 quantity squared. And prime is 96.9 e to the 0.12 t over e to the 0.12 t plus 8.5 quantity squared. Let's put that into the calculator here. And we get, I'm just going to do alpha y equals n over d. If your calculator doesn't do that, make sure you have parentheses around your numerator, parentheses around your denominator. 96.9 e to the 0.12, and use an x there. And then down here I have e to the 0.12x plus 8.5 quantity squared. And then they want me to find that growth rate at some different times. So I'm going to use my table for that. When we have t equals 5, t equals 10, and t equals 30. And I think these are measured in days. Weeks, sorry. These are measured in weeks. So n prime of 5 is 1.657 words per minute per week is the improvement there. And then n prime of 10 is 2.303 words per minute per week. And n prime of 30 is 1.744 words per minute per week. So you can see that it goes up and then it starts to still increasing, but it's increasing at a decreasing rate. So we have this point of diminishing returns that we might be interested in there. So if we were to see if we can get the graph to show us what that looks like. Again, this is the graph of n prime. So I'm looking for where n prime maxes out here, which is right there. So that's my largest marginal return is going to be after almost 18 days. So after that, I'll still be increasing, but I'll be increasing at a decreasing rate. All right. Let's look at, I think I have one more to show you right now. I might have some others to come back to in a little bit. So let's look at a probability problem to wrap things up for right now. This is number 49. And it says, in a recent year, the mean SAT score for the College Board for college-bound seniors in mathematics was 513. So they use mu to represent that because that's the mean of all people who took the test. And the standard deviation sigma is 120. That's information from the College Board. It doesn't say for what year. Assuming that the data can be modeled by a normal probability density function, where we need to know the mean and the standard deviation. If we have that, then that's going to be equal to 1 over sigma times the square root of 2 pi times e to the negative x minus mu quantity squared over, I think this is sigma squared, if I remember correctly. But you have a normal PDF. feature in your calculator that you just need to pass it mu and sigma here, which is what I'm going to do, and make it draw it. So we have second distribution. There's normal PDF right there, and we're just going to let x be x. And our mu, we were told, was 513. And our standard deviation, we were told, was 120. The only time that you're going to use normal PDF and the calculator is like this, where you want to put it into y equals, and you want that x to be a variable. And I'll zoom 0 on this and zoom out, so you can see that it is a we should be getting a normal curve here. Why are we not getting a normal curve? There it is. So there's a normal curve right there. And let's center this on our score that we want. So let's go -3 times 120 plus what was our mean? 513, and then 3 times 120 plus 513. And we want to go by scale, by increments of 120, so we can see the stations. We're going to go from there to let's go up some here. So close to 0, doesn't quite get there. Let's go up to, does this say that the output is percentage, right? So too big. There we go, something like that. All right, there's our normal curve. So we graphed it, right? We found the function for it. So y equals to 1 over 120 root 2 pi e to the negative x minus 513 squared divided by, and sigma was 120. I guess that's 2 sigma squared. Sorry, 28,800 is what goes there. So that we just got times 2. So I get the 28,800. And then find the derivative of the model. Oh, yay. So y prime is going to be a, just leave this out front because it's a constant. And we're just dealing with the derivative of this exponent here. That's negative 28. 800 negative 2 times x minus 5, 13, and then e to the negative x minus 5, 13 squared over 28, 800. 2 goes into here and makes this 14, 400. And y prime is going to be 120 times 14, 400 is 17,28000 square root 2 pi. This is a negative, and this is x minus 5, 13, e to the like that. And so then if I go into look at that function, negative x minus 5, 13 divided by 172,800 times square root of 2 pi. And then all that denominator is closed up, so times e to the negative x minus 513 e squared divided by 28800. And let's zoom 0 that, right? So now I'm interested in, does f prime of this, so this is f prime, this is f of x, is f prime greater than 0? For all x less than mu, and f prime less than 0 for x greater than mu. Well, that makes sense because it looked like this, and there's mu where it leveled off and it's going up and then coming down. But let's prove that here. So for x less than mu is 513. So if x is less than 513 here, then this is a negative and this is a negative. So this is a positive times a, and then that's always going to be positive when I square that. So that's a negative, but this is always e to something is always positive. So a positive times a positive is a positive for u equals 513, right? So we're increasing on this interval. And for greater than mu here, then this is going to be a positive times a negative is a negative. All this is positive down here. That's always going to be positive because it's e to some power. And so that's going to be negative, and this is going to be decreasing on this interval here. So we're positive here. There's mu right there, and we're positive slopes for x less than mu, and we're negative slopes here for x greater than mu. I can figure out that 0 right there is at 513, which is mu. All right, I think I'm going to stop there for now. I have a few more problems in this section to come look at, but each of these problems just takes so long, and this has been about an hour already. Come back and look at the last, I think, 3 problems in another video coming up here. So, or I may just cut it there for this section and say that we've done enough of them and leave. That's what I'm going to do. And I'll leave 51, 52, and 53 for you all to try on your own. When I come back next time, I will start looking at section 4.5. See you for the next video.